Here's a problem about some moving boats. And I wanted to go through this problem because whenever you first see this, you kind of automatically think, oh, it must be a related rates problem because I've got some moving boats, right? So, in fact, this is not a related rates problem. It's an optimization problem. So let's take a look and see how we know the difference and how we know what they're asking. So the question says, a boat leaves the dock at 2 p.m. and travels due south at the speed of 20 kilometers an hour. Another boat has been heading due east at 15 kilometers an hour and reaches the same dock at 3 p.m. So far, so good, right? You've got a bunch of moving boats. You're thinking related rates. But the question is, at what time were the boats closest together? So they're not asking about the rates of the boats changing, right? Or how the distance is changing between the boats. They're asking for a minimum. The boats are close. When are the boats closest together? They're asking you to minimize the distance between the two boats. So that's the difference. Rather than asking about the change in the rate or how fast the boats are moving further apart or whatever, they're asking for a specific moment in time where the distance is minimized. So let's see how to go about that. It's kind of a little bit different because you want to think about, when we think about distance, right? We already did an example with distance formula, right? Your distance formula was the square root of the difference between the x coordinates and the difference between the y coordinates, right? And we said to make our lives easy, we can actually minimize the square of both sides because the square and the square root also are always increasing functions, so they're not going to change the location of that maximum, okay? Which is fine, but they didn't really give you the distance in the problem exactly, so you sort of have to figure out where the boats are and what that distance might be. So we kind of have to do a bit of setup here. So let's figure this out. I'm going to put a coordinate plane, and this is my dock, right? And I'm going to start t equals 0 at 2 p.m. So my first boat leaves this dock and moves south, right, at a rate of 20 kilometers an hour. Okay, t equals 0 at 2 p.m. And I'm going to use t in hours. Okay, so on this coordinate plane, if this is the y direction and this is the x direction, the position of, we'll call it boat A, position of A at time t, obviously it's t times how fast is it going? 20. So 20t, right? But that is actually on the coordinate plane, that's the y coordinate, and because he's going due south, the x coordinate is always 0. So that's one thing that's kind of different in this problem. The reason I'm putting it on a coordinate plane is specifically so I can use the distance formula, because the distance formula is given to me in x and y coordinates. So if I can find the position of my boats in x and y coordinates, I can just stick it into here. Okay? So fine. That was the easier one, right? A just starts at 0 and goes. Now, where is B going? I don't know. B is over here. Oh, we don't know exactly. We got to figure that out. Okay? So B is going this way. They don't tell you where B is at 2 o'clock, but they tell you that B is heading due east, so B is going, I did the wrong way. Yeah, B is heading east. This is east. Okay. Woo! B is heading east. I'm glad I noticed that. Right? Yeah. So B is heading east at 50 kilometers an hour. And B makes it to here at 3 p.m. So 3 p.m. is an hour later than t equals 0. So 3 p.m., right? 3 p.m. is t equals 1. Okay? Now, if he's heading a steady 15 kilometers an hour, that's going to tell me that at t equals 0, he was sort of 15 kilometers this way. So it would actually be negative 15, right? So this would be negative 15 at, he was 15 kilometers west or at x equals negative 15. Okay, so position of B then at time t, we kind of have to think about it. He starts at, when t equals 0, he's starting at negative 15, and A is starting at 0, 0, right? And then they're going like this. So at time t, he's starting for x as negative 15, but then as time goes, he is moving this 15t, right? So he is going plus 15t, right? But that's, again, along the x direction, he's going due east. In the y direction, he's always going 0. Okay? So, as we start here and here, and as time moves, we move this way, right? Because at time t equals 0, we're here. At time t equals 1, we would be here. And of course, A would be at 20. And presumably somewhere in the middle here, there's some minimum distance between the boats, which we're supposed to find what that time is. Okay? So that's going to be the setup. Now notice again, the reason I wrote both of these, and we'll call this can be x1, y1, position of A, and B can be x2, y2. Right? So we can figure out putting that into RD, or d squared. We can then take the derivative and find the minimum. So actually that part is really easy, right? Because if I take my distance squared, x squared, x2 minus x1 squared, plus y2 minus y1 squared, this would be minus 15 plus 15t squared, and then this would be 20t squared. All right, so I'll work that out in a second. But I just wanted to leave this up for a second so you can see A, B, and then we're basically doing a distance formula between these 2 points at any time t. T then is our variable because we were able to write both the x and y coordinates of the boats in terms of the variable t. Okay. We'll call this big D. The derivative with respect to t. All right, maybe I'll just, instead of doing that, I will do that first, but let me work this out first. Okay, this is going to be 225 times t minus 1 squared plus 400t squared. So this is 225t squared minus 450t plus 225 plus 400t squared. So eventually, so this is just like simple arithmetic at this point. Thank goodness, right? Derivative, easy. 625 times 2 is going to be 1250, right? 1250t minus 450. Linear, I'm going to set that equal to 0. I have t equals 450 over 1250. So that's 45 over 125. If I take out 5 times 25, so this is 9/25 of an hour. Okay? Now, double checking, is that in fact a minimum? Here's my point. If I put it in this line, if I take to t equals 0, obviously that's going to be a minus. If t equals, say, 1, that's going to be a plus. That is my minimum. Okay. And that's what they asked for. They asked for what time, so I have found the answer.